Welcome to lesson 9.4, Perform Rotations. So as we go through this lesson, the goal that you want to keep in mind is going to be able to take these rules for rotations and rotate not only points, but also different figures or shapes. So when you think of a rotation, you can think of a rotation as a type of transformation in which a figure is turned about a fixed point called the center of rotation. So rotation you can think of as turning or spinning something around a fixed point. And that fixed point would be the center of the rotation. Rays are drawn from the center of rotation to a point and its image, and that forms the angle of rotation. So that's how we measure our rotation, is we would line up a point on the pre-image and draw a ray through that, and then we would draw a ray through a corresponding point on the image, and when we measure the angle that those create, we get the angle of rotation. So a rotation about a point, in this case we'll call it point P, through an angle of x degrees maps every point Q in the plane to a point Q prime so that one of the following is true. So what that's saying is no matter what our rotation is about a point, if it's the rotation of the same degree measure, that's going to take every single point from our pre-image and map it onto a point on the image. And one of the following properties would be true. If our point is not the center of rotation, then the original distance from the center of rotation to that point would be the same as the distance from that new rotated point to the center of rotation. So in other words, if we look down here, point Q, after we rotated 40 degrees, Q prime is still the same distance away from point P. And the measure of angle QPQ is going to equal, or QPQ prime, I should say, equal our degrees. So if I drew in this angle and measured it from Q to P to Q prime, it should measure the same as our rotation angle. Or the other property, if Q is on the center of rotation, P, so if we're rotating something that's on our point, then the point wouldn't move. Our rotation image is the same as the original pre-image. So a 40-degree counterclockwise rotation is shown over here at the right. Rotations can go clockwise or counterclockwise. In this chapter, we're only looking at counterclockwise rotations. So everything would be going, if this is our original, it would be going in a counterclockwise direction. Now, for example 1 and 2, you can see I already drew in the rotations and drew in my different rays. So I'm going to read through these 4 steps, and then what I want you to do is to pause the video and watch the video showing you how to do this construction. And yes, the construction is creating the rotation. And there will be 2 ways that I show you how to do it. One way will be using a ruler or straight edge and a protractor. And the other way would be using a protractor and a compass. Either method, you still need the protractor. So our 4 steps are pretty simple. If we know the point that we're rotating about and we have our original figure, step 1 is to start with a ray from our center of rotation, point P, through a point on our pre-image. So P through A. Then what I want to do in step 2 is I'm going to measure 120 degrees from that ray, and then I would draw my other ray, which is P to A prime. And then what we need to do is measure the distance from P to A, measure along this new segment to tell us where A prime goes. Because A prime needs to be the same distance away from P as it was originally. So I'll show you those 3 steps in our construction video. And then step 4 is simply to repeat those 3 steps for every vertex that you have. And then we go back in, connect the dots to create our shapes. So example 1, part A and B, pause the video now, watch the construction video showing you how to do this process, and then come back and try these 2 in your notes. You don't need to use all the different colored rays or segments. I just did that so you could tell that the pink segment here went with the pink segment here, orange with orange, and blue with blue. So pause the video, watch the constructions, come on back, and we'll move on to our next part. So our next part are rules specific to rotating about the origin. And what you want to remember is the origin refers to point 0, 0 on a coordinate plane. So you can rotate a figure more than 180 degrees. The diagram over here shows all things considered our original point A here. So they're showing rotations of point A 130 degrees here to A prime. They're showing a rotation of A 220 degrees down here to A double prime, and a rotation of A 310 degrees all the way over here to A triple prime. If we would rotate 360 degrees, we're right back to our original coordinate. Now, the reason that we're covering this is we actually have special rules to find the coordinates after rotating a point 90 degrees, 180 degrees, or 270 degrees about the origin or around the origin. So these special rules only work if we're rotating around the point 0, 0. So let's look at those special rules. So our coordinate rules for rotating about the origin. So if our original coordinates were A, B, and we're rotating all these counterclockwise. So for a 90-degree rotation, AB becomes negative BA. So if our original point was 5, 4, our new point would be negative 4, 5. For a 180-degree rotation, the original coordinates AB become the new coordinates opposite of A, opposite of B. So if my original coordinates were 5, 4, my new ones after a 180-degree rotation would be negative 5, negative 4. And then if we're rotating 270 degrees, our original coordinates AB become our new coordinates B, comma, opposite of A, or negative A. So 5, 4 would become 4, comma, negative 5. And those would be your rules for our 3 special types of rotations about the origin. So example 2, part A, is talking about one of those special rotations at 270 degrees. So we're going to use our rules. So if our original points were A, B, the 270-degree rules tell me B comes to the front, A moves to the back and becomes a negative. So first off, and I did not graph this as a quadrilateral, so you can change your directions here. Get rid of quadrilateral, change it to triangle, RST. Because you can tell that obviously from looking at my graph, I did not graph point U, so I just did triangle RST. So here, graph triangle RST. R was at 3, 1, S was at 5, 1, T was at 5, negative 3. So the blue triangle here, my original triangle. Now, using our rules for the 270-degree rotation, if R's original point was 3, 1, R prime would be 1, comma, negative 3. For S, original point was 5, 1, so our new point, S prime, would be 1, comma, negative 5. And for T, the original is 5, negative 3, so T prime would be negative 3, negative 5. So then we want to graph those 3 points. So we'd graph R prime. Over 1, down 3. Graph S prime. Right 1, down 5. Graph T prime. Right 3, down 5. Connect your vertices, and now you have rotated triangle RST 270 degrees about the origin. Now part B. So in part B, we are graphing triangle JKL. So let's start with that. So graph JKL. J is at 3, 0, K is at 4, 3, and L is at 6, 0. So J over 3, L over 6, and K over 4, up 3. So there's our original triangle. Now the rules for a 90-degree rotation are, if our original coordinates are A, B, it becomes opposite of B, comma, A. So 3, 0 for J becomes J prime 0, 3. K's 4, 3 turns to K prime negative 3, 4. And L at 6, 0 turns to L prime 0, 6. You'll notice with J and L, when the 0 came to the front, 0's neither positive or negative, so it just stays the same. So then we graph our 3 new points. J prime up 3, L prime up 6, K prime left 3, up 4. Connect our vertices, and we have now rotated our original triangle 90 degrees. So then we get to this concept here about rotation theorem. And our rotation theorem simply says that a rotation is an isometry, meaning if we're rotating ABC to A prime, B prime, C prime, they are still congruent triangles. All right, now down here, and that ST up here is really annoying me, so I want to get rid of that. There we go. Hopefully it stays away this time. All right, then example 3. Example 3 is telling us the quadrilaterals rotated about P. Find the value of Y. So in order to do this, we want to look at our original quadrilateral here. It has a side of 8, side of 6, side of 3x plus 1. I don't know the fourth side. It rotates over here 100 degrees to its image, and it has a side of 2x here and 5y here. They want us to find the value of y. So what we want to do is match corresponding sides. So in this case, the 5y corresponds with the 3x plus 1, and the 2x down here corresponds with 6. We know the corresponding sides are equal. So 2x would equal 6, meaning x equals 3. Divide both sides by 2. We also know 5y here equals 3x plus 1. So 5y equals 3x plus 1. So if we take this 3 and put it in here for 3x plus 1, we can solve for y. So 5y would equal 3 times 3 plus 1, meaning 5y equals 10. Divide by 5, and y equals 2. So our value of y would be 2. That ST up here just keeps coming back on my screen. Oh well. Then, example 4. Find the value of r in the rotation of the triangle. So our original triangle here rotates 110 degrees, and in this case they went clockwise, but that doesn't matter. We can tell by the way they drew the arrow. Our original is here, new one's here. So if we're rotating that, matching up corresponding parts, the 12 here would match up with 2s here. So 12 equals 2s, divide by 2, and we know s is 6. Then I know that this side, 3r, matches up with the 2s plus 3. So we would set that up, 3r equals 2s plus 3. And now that we know s is 6, we can put that in here, substitute it for s. So 3r would equal 2 times 6 plus 3. 2 times 6 is 12, plus 3 is 15. So 3r equals 15. Divide both sides by 3, and the value of r is 5. So the key to this lesson would be realizing that when we rotate figures, they remain congruent, meaning it's an isometry. We have 3 special rules here for our rotations of 90, 180, and 270. And then make sure you watch the construction videos on how to do ones like example A and B here for part 1, when we're not dealing with the coordinate plane and rotating about the origin.